I know that it's really low in its velocity. In fact, it's lower than this number, so this has to be a negative number. So this tells me this is a really cold environment. And so now I can begin to solve for this number. And if I then subtract, I get a negative 31 here. And this would be meters per second, which would then, of course, cancel off. And so now I can get what is the temperature. So finding my calculator here, I have a negative 31. I can divide it by 0.61. And so this environment must be about a negative 50.8 degrees Celsius. And if you remember the lab we did on the air thermometer, we used that dry ice, which was way down there at about negative 65, negative 70. So the only thing I can come up with is maybe this is, a chamber that's filled mostly with air, and somebody threw a bunch of dry ice down on the floor, and it's cooled down the room, not all the way down to the temperature of the dry ice. It's not quite that cold, but it's getting close to it. And so that's kind of what would be a way to describe what maybe is going on in here. A very, very cold environment filled with air would give me a low speed like this. But the point is, the speed goes right to the temperature, and they go hand in hand. Now, of course, the other part of this question was really back over to here. What is its wavelength? Its wavelength then would be velocity divided by frequency. And so I want to point out here that what has changed is the velocity, but what has not changed is the frequency. Remember, the frequency of this tuning fork, right here, was determined, as we talked about earlier, by the stiffness of the metal, which is what kind of material is it made out of, aluminum. How long is it? That's its inertia, and of course its thickness. Well, I guess the material aluminum, its thickness is how stiff it is, and then how long it is its rotational inertia. And so if I take this into a cold environment, it's the same thing. And so I take this, it's going back and forth at the same rate. I take it into a cold environment, it goes back and forth at the same rate. Now, granted, because each little pulse it makes doesn't travel away as fast, in a warm environment, this pulse would go way over here before the next one, and I would have a wavelength this far. But in a cold environment, this little pulse would only go to here. And so I'd have a smaller wavelength. And that's what we see here in the numbers. I have a smaller wavelength. Now, a small subtlety here, I should point out, we know metals get a little stiffer when they get cold. So I am ignoring that. Obviously, if we went in a cold environment, it'd be a little bit stiffer. It also might be hitting more molecules, and that might have an effect. But for the most part, it would really stay the same frequency. And so I'm going to go 300 divided by 1024. And now I get a wavelength of 0.293 meters, or if I write it as 29.3 centimeters, I would get that different wavelength that I was talking about. It is shortened up a little bit by about 4 centimeters. And so that's the neat thing about producing our sound. And really, those are some of the most mathematical questions that the author asks in this chapter. But some more fun conceptual ones goes back to what I'll call the generation or the creation of these sound waves. Mostly so far I've been showing you the speaker system, that the paper diaphragm moves back and forth, or the cell phone has a little piezo electric down here in the bottom, and so just behind there's a little metal piece that gets bigger and thinner as it goes back and forth here. And so that's true. And there are other ways of making sound. In fact, maybe you can hear that. Let's see if I can get a metal one here. Maybe I'll go to a higher frequency one. This one, believe it or not, actually has the same frequency as this one. I say believe it or not, because you look at it and you go, well, the metal is thinner. It's still aluminum, but it's thinner. Sure, so it's not as stiff. But it also doesn't have as much inertia. See, look, they're thinner and they're not as long. But I wanted the metal base here because I'm hoping you might be able to pick this up on the lapel mic. What if I hit this? Okay, and pick that up. But what if I touch the base on this wood? Can you hear it get a little bit louder? And you may not be able to, because the good thing about these lapel mics is they auto adjust for intensity. So when things get louder, it kind of turns it down automatically, and then things get softer, it turns it up. And so the lapel mics are kind of hard to pick up the louds and softs. But I'll try it again. And so I'm going to try this. And so here. But what I'm trying to convince you of is that I could use, and the reason it gets louder is when I touched that metal onto this piece of wood started shaking. And so instead of just hitting the molecules that are on this piece of metal going back and forth, I have this whole surface. Now, it probably didn't shake the whole surface, so I'm kind of exaggerating with the whole surface. But at least around this area where this piece of metal is, it shakes it back and forth. And it makes it oscillate. It makes it vibrate. And I point that out because you are probably also familiar with what we would call stringed instruments. How does a string instrument work? Well, of course, the first thing is you start with strings. And so here is a very poorly tuned guitar. But you'll see why it's poorly tuned here real soon, is that if I then pluck just one string, this string vibrates back and forth. And what is really nice is this box. Real thin piece of wood. And so when I have a string going back and forth, and that one barely changed, so I doubt if you picked up really anything on the lapel mic. But the idea here is you begin or you create your sounds with the string. And this then amplifies that, if you will. So it's not so much that I'm really interested in amplifying, but just pointing out that the amplification, the physics of it is the amplitude, the number of molecules you're hitting. And so that box really does that. But the sound itself is actually generated by the string. Now this old guitar, this one is broken. Let me... Yeah, maybe I'll do the G string here. But if I pluck this and reduce the tension, hopefully my lapel mic is picking up. Now I'll tighten it up. And see, what I'm doing is, from the physics, is giving it more tension. And as I give it more tension, it would then be, in a sense, stiffer. And it's going to be shaking back and forth. It's going to be at a higher frequency. And so that's how we tuned the guitar. We change the tension. We're making it stiffer. And so just like these tuning forks that I was showing you, a guitar has those two important principles. One is how stiff is it? In this case would be the tension on the string. And then what is it that you're shaking back and forth? That would be the inertia. So over here on the guitar or any stringed instrument, you will see, whoops, you will see that the strings that play the low notes, like that one, so I go to the top G string and then the bottom G string, and this happens to be a real thin string, it's got very little mass. And so it can go back and forth really fast. So it plays a high frequency. And this one plays a low frequency. And of course there's another effect. I think you can kind of see it here. What if the string was shorter? Now, I don't mean actually cut it shorter, but what if I just took my finger and clamped down here on the 5th fret? 4th, 3rd, 2nd, 1st. You see, as I get closer in here, I'm making the string shorter. That's kind of like making it stiffer. And it's being held tighter. And as it's being held tighter, it's going to shake back and forth faster and faster. And so you play a string instrument by essentially changing its length. And so again, you can tune it. Now, within reason, you can only put so much tension on it. That's why for the low notes, you have to have a fatter string. And for the high notes, you have to have a thinner string. So you can play with the density there. But then once it's tuned, you can essentially change its length. And so the shorter they are, you're going to think of it as more stiff. And if it's more stiff, it vibrates at a faster rate. And remember what we've been saying this whole chapter is that that rate at which it goes back and forth is its tone. And that's why if you know anything about instruments, if I were to ask you, oh, give me a stringed instrument that plays really low tones. And maybe you go, huh, what's a good example of that? Well, have you ever seen one of those bass? You know, the violin is this short thing that goes on your shoulder. The cello is a little longer. And the bass, to play it, you actually have to get up on a step stool. And the strings are so long, and you got to play it up here and strum it down here. And if you look at somebody playing that, not only is it really long, the strings are really fat. Now, not quite that fat, but they are fat. And they're really loose. If you walk up to it and just touch them, they shake and they jiggle. They're not taut. And so all of those go into playing low notes. Whereas the violin, just the opposite, right? You could get, the strings are only this long, and they play high notes. And you can even make the string shorter and play higher and higher notes. And so where you put your fingers there. And so that's kind of the physics, if you will, of making sound with a stringed instrument. Well, what about the reverse of this? I shouldn't say the reverse. How do we make sounds in a trumpet, a trombone, what we call a wind instrument, a clarinet? I don't have anything fancy, but this recorder. And if I blow in the recorder, it plays a note. It plays a tone. And why? Well, okay. Then from here to here, the size of this is very similar to the size of the guitar string. So the shorter it is, the stiffer it's going to be. Or you could also say, look, you're clamping it down, so this is a node and this is a node, and so this is one wavelength. And so you bring it in closer and closer, the wavelength gets smaller and smaller and smaller. And so this is exactly what you see with the recorder. And the whole reason the recorder or the clarinet or the saxophone, they have this long thing with all these buttons on them, so you could essentially change the length of it. And so in this one, if I were to start here, I'd play a note. If I were to cover the next one, I'd play a different note. If I play the next one, see, see what notes, and notice as I cover more and more of them, right? This is a lower note. Then say this. Because against those holes is what comes out. And so right now, you could think of it as this is the length of the tube here. And so this is a small wavelength, and this is a big wavelength. And the big wavelength then, of course, would correspond to a low frequency. And that's the pitch you hear. And so that's how our wind instruments work. Now, I'm not a real good musician, so don't laugh too hard at me. But here's my favorite. You can hear the different notes. Here's the E. Yeah, okay. So there is what I learned in 5th grade, way back again when the Earth was cooling and the dinosaurs were walking on the Earth. But that was what we learned in our class, a combination of physics and music, where we would say, hey, look, why does it make these different sounds? In fact, it's why I kind of like to bring this one up next. This one is a whistle, I guess. But this is kind of like the trombone, and it'll give you an idea that the frequency really is created by the size of that tube. You could say that the size of the tube is one wavelength. So this you can't see, but it has a plunger in it. And so if I pull it in like here, the distance from here to the plunger is only like that. I'll bring it even more. There's a high frequency, really short wavelength, and therefore really high frequency. Or I can pull the plunger out, or a combination. And so the frequency changes. So frequency is really decided by the size of this tube, by the size of the string. This is how the sound is generated. It's trapped inside of here. And so now I think you can imagine how these wind instruments work. Why the trombone, low, high, and you change it. Or the trumpet, you press the valves and they will go through a different path, and that path will be a little bit longer. And if you think about what musical instrument, what wind musical instrument, oh, how are we doing on time? Oh, I guess it's about time we got to wrap this up here. So real quick here, what musical instrument plays a low tone? And I guess one of the things that come to my mind is the tuba. Or the marching tuba is a really good one if you've seen bands. Because that's that big thing that has a big old horn up it, and then the horn itself wraps around the marcher before it comes out. That is really long, and that plays some really low tones. Oh, what's the wind instrument that plays the high frequencies? How about a piccolo? A flute? Now, piccolo's a little smaller than a flute. I don't have anything to kind of illustrate it. But I do have this. This is my homemade sound instrument. It's an empty bottle, although it's important to point out, no, it is not empty. It's got air molecules in it. And this is how deep it is. And so if I blow in it, it makes a particular tone. What if I were to shorten it up? And in this case, I'll shorten it up by really not making the plastic any smaller, but filling it with water. So now the sound is trapped in a shorter sound tube. And so it's higher. I thought it would be a little higher than that, so let me go a little bit more. And then I better call it quits for today here, and we'll pick this up tomorrow. But this is a high frequency. Make the tube a little longer. A little lower frequency. Make the tube a little longer. Lower still. And as long as I can make this, And so those are the different tones I get. It's also why, and we'll have to call it quits here for today, but I've got a big tube and a short tube. And one's in between. And all of them have then a slightly different tone to them. And we've actually cut them and got them just right so that they'll hopefully play a whole range. And just so that I don't forget and have to do this all tomorrow, let me try this one again. Yeah! And so that's our tones. Well, better cut it here. Tomorrow we'll come back for lecture 1, and let's finish up this chapter 16, and then we'll get started into our light wave 17. All right, see you then.